Let's look at a few more integration by substitution examples. One question that I get a lot before we hop into those, though, is, well, how do I know when I need to use integration by substitution? What tells me that I need to? And the short answer is you'll kind of just have to use it. If you think about our integration techniques that we've talked about, we've really only talked about integrals of, say, e to the x dx, integral of 1 over x dx, and the integral of x to the n dx here. If I look at something like this, here I have the indefinite integral of the cubed root of 2x minus 4. This is starting to get a little bit more complicated. This doesn't really look like any of my three base cases. It's not an exponential. It's not it's not 1 over x. Now, x to the n is probably the only possibility that it could be. So maybe you say, okay, well, let's try rewriting this as 2x plus 4 to the 1/3 power dx. The problem is you don't have x to the n, you have 2x plus 4 to the n. So that's kind of what tells me, hey, we have to use integration by substitution here because this one's going to be a little bit more complicated. So as soon as you identify that inside part is not just x, it's actually this 2x plus 4, that is going to be your u. U is 2x plus 4. Du then, remember we can find du here by just taking the derivative, which would be 2 times dx. We would have to multiply by that dx here. So this piece right here, this 2x plus 4, I know that that is my u. Du, I see I have 2 dx. Well, this is kind of a problem here. I really only have this dx here. So I have this extra factor of 2 that maybe I'm not quite sure what to do with. And this will happen from time to time where we have this extra leftover factor and we're not quite sure what to do with it. I'm going to go ahead and just force this equation. I'm going to force dx to be on the right-hand side. So I'm going to treat this like an algebra equation. I'm just going to go ahead and you can either think about it as multiplying both sides by 1/2 or dividing by 2. I think it's probably easier, and I'll explain why in a little bit. I think it's easier to multiply by 1/2. So that those two cancel, so I have 1/2 du equals dx. So that dx, when I take out this dx, I can replace it with 1/2 du. So this is what I meant earlier by solving for other parts of your integrand, where we had some extra stuff up here. Our du didn't quite look like everything else in the function, so we had to divide it, or in this case, multiply it by some constant. And usually that's all it is. And most of the time, if it doesn't match up exactly right, you're just going to have to multiply or divide by some constant. So let's make our substitution then. So we have the indefinite integral of, this is really u to the 1/3 times 1/2 du. So okay, I just took out, just to emphasize here, took out 2x plus 4, replaced it with u. I took out my dx and replaced it with 1/2 du. So now, maybe this 1/2 is a little bit concerning to you, right? This looks pretty straightforward, I think, except for this 1/2. But remember that 1/2 is just a constant multiple, and that's why I wanted to stress, hey, I think it's easier if we multiply here by 1/2, because I think it's easier now to see, oh, well, I can just take this 1/2 and factor to the front of my integral so that I don't need to worry about it. So I'm going to rewrite this as 1/2 times the integral u to the 1/3 du. And now this is a little bit more, I think, easier to manage. It just looks a little bit cleaner. We don't have to worry about that 1/2. I didn't just get rid of it, I just pulled it out to the front of my integral so that I wouldn't have to worry about it. So now I should be able to evaluate my integral. So let's do that. So let's see, 1/2 times, I'm going to add 1 to my power. This is really u to the 4/3 if I add 3 over 3. And here I don't want to have to divide by a fraction. It's just ugly, so I'd rather multiply by the reciprocal. So I'm going to multiply by 3/4 plus my constant of integration c. And then for my last step, I'm just going to simplify this a little bit. I can multiply these two fractions. I just multiply straight across. So 1 times 3 is 3. 2 times 4 is 8. I have 3/8. And I want to take out this u and replace it with my 2x plus 4. So I'm going to take out that u. I have 2x plus 4 to the 4/3 power. And of course, plus my constant of integration c. Here is my antiderivative. So hopefully it feels really similar to the types of problems that we were looking at earlier. We just have this extra constant multiple that we now have to worry about. Let's look at another here. Next up, I have the integral of t cubed plus 4 to the 6th power times t squared dt. So here, I look at this again, it's similar to the last example in that I have t raised to some power, but it's actually not just t raised to some power, it's t cubed plus 4 raised to some power. So I'm going to choose this piece right here. I'm going to choose my u to be t cubed plus 4. So as soon as I find u, I should also find du. Du would be 3t squared dt. And I say, okay, let's look at this. Here I have t squared dt. I see the t squared dt. That's what I want right there. So I need to get rid of that 3. So again, you can either divide it by 3 or you can multiply 1/3. It's up to you. I'm going to multiply both sides by 1/3. And that will give me 1/3 du is equal to, oops, not 3t squared because these cancel. It'll leave me with t squared dt, which is exactly what I want. So when I make my substitution, this blue part that I've underlined, this is my u. And the red part that I've circled right here, this is going to be 1/3 du. And I like kind of circling this and making a notation with the original problem because I think it makes it a lot easier to look at and say, okay, now I understand exactly how my substitution is going to look once I'm done. So let's see, I should have the indefinite integral of u to the 6th power times 1/3 du. So I can say times 1/3 du, but I know I'm going to want to do the same thing I did with this 1/3 last time. I'm going to want to factor that out just because I think it makes the rest of the problem easier. So what I will do oftentimes right away, rather than writing as 1/3 du, I see this constant multiple of 1/3. I'm just going to go ahead and factor that out right away. So 1/3 times the integral of u to the 6th times du. So I just skipped a minor step here in kind of substituting this in the exact order that it's written in because I know I'm going to want to factor out this constant multiple. Why don't I just get it over with right now? So hopefully we end up with something that is easier to integrate here. And this looks a lot easier to integrate. This is a power rule. So I have 1/3 times u to the 7th divided by 7 plus my constants of integration c. And so this is equal to, let's see, 1 times u to the 7th, this is u to the 7th. 3 times 7, this is 21 plus c. And then my last step, of course, I want to take out my u, replace it with t cubed plus 4. So this is really t cubed plus 4 to the 7th power divided by 21 plus c. here is my antiderivative. All right, so let's look at one. Actually, I think I have two more examples here. Here I have the indefinite integral of x squared plus 1 quantity squared dx. So you might look at this and say, all right, I see your tricks, Mr. Huber. This is not just x to some power, this is x squared plus 1 raised to some power. And we say, okay, I'm going to try substitution here. I'm going to choose u equal to x squared plus 1. So du would be 2x dx. We actually have a tremendous problem right now. And I'll circle it. It's this guy right here. Because I know x squared plus 1, this is my u. So this is u. All I have left over to substitute for is dx. Now, you could say, okay, well, let's just handle this like we always have, right? I'm going to multiply by 1 over 2x. I'm going to multiply by 1 over 2x. So I would have 1 over 2x du is equal to dx. So, okay, maybe that works. So you'd say 1 over 2x dx, du, excuse me, is what I'm going to substitute in. So I would say, okay, well, this is really u squared times, well, the 1 over 2x, I can factor out the 1 over 2, but I can't do anything with that x, because remember, I can only factor out constant multiples. X is not a constant. X is a variable here. And so maybe you say, okay, well, let's just leave it in. Well, we'll figure it out. Times du. And I have a really, really big problem here. And that's that I have this integral now written in terms of u and in terms of x. This is something you really, really, really want to avoid. You don't want to mix and match your variables here. You don't want to end up with something in terms of two variables, because that's even worse. So what that tells me is I've either made a mistake somewhere in my substitution, and I can look at this and it looks like a relatively straightforward substitution. I don't see any errors. Or I have tricked you, and this is actually not a substitution problem. I actually cannot perform this integral using substitution. I just can't. So I have to think about other ways to deal with this. This is not a substitution problem. And this is tricky. This is not a substitution problem. So I need to think about, well, what can I do with this then? And I notice, hey, my exponent's only a 2. I can just go ahead and FOIL that out. X squared plus 1 times x squared plus 1 dx. We can go and FOIL this out. This is really going to be x to the 4th plus, 2x squared plus 1 dx. And then, okay, now I can just do the power rule. It's just a polynomial. So this will be x to the 5th over 5 plus 2x cubed over 3 plus x plus c. So this is my solution. This is my antiderivative. So be very careful. If you try substitution and it doesn't work, first you'll want to go back and double check your work. If that doesn't work, if you can't find any mistakes, go back and look at the original problem and say, is there another way that I can simplify this? I promise you, I will ask a question like this on the exam. I always do. So I'm telling you right now, I'm going to try and trick you on this exam. This is a trick question. It looks like a substitution problem. You see the parentheses and say, okay, I think substitution, but substitution will not work. So be careful with these problems. And let's look at, I think I've got one more example here. Yes, I do. Here I've got the indefinite integral of t cubed over t to the 4th minus 2 to the 5th power dt. And I say, okay, well, this, I see the parentheses, I see t to the 4th minus 2, that's kind of the factor or the piece of this with the highest power of t. So I'm going to choose u equal to t to the 4th minus 2. And then du, of course, will be 4t cubed times dt. So I see, well, I have t cubed dt. I see t cubed dt, which this isn't as big of a problem as we had in the last one because I can just get rid of the 4. That's the piece that I want to get rid of. So I'll get rid of that by multiplying both sides by 1/4. So I'll end up with 1/4 du is equal to t cubed dt. So when I take this piece out, I'm going to replace it with 1/4 du. And then this blue part over here, that's going to be u. So all right, let's make our substitution here. First thing I'm going to do, that 1/4, I don't want to have to take an extra step to factor that out, so I'm just going to go ahead and do that. Oops, not 1/6, 1/4. I'm going to do that right now. You can put that du in the numerator if you'd like, or you can just say you'll have a 1 and then put the du off to the side. It doesn't really matter which way you put that. I'm going to leave it as 1 over du just since, or 1 times du since I already have that. And then in the denominator, I have u raised to the 5th power. So this is the integral that I would like to evaluate. I do have a slight problem, though, and that is I can't integrate this function while u to the 5th is in the denominator. If it was 1 over u, then yeah, sure, I could do that. But 1 over u to the 5th, that's not going to work. So I do need to just take a step and rewrite that. This will be 1/4 times the indefinite integral. This will be u to the minus 5 du. So let's see. I will say 1/4, add 1 to the power. This will be u to the minus 4. Divide by my new power of negative 4. Plus, of course, my constant of integration c. So let's see, 4 times negative 4, this is really over negative 16. I will take my u, which we said was t to the 4th minus 2 to the negative 4th power plus c. So we could leave our answer like this. Or if you're me and you just really don't like negative exponents, we could also say this is negative 1 over 16 times t to the 4th minus 2 raised to the 4th power plus c. Either of these will be just fine. Doesn't really matter. In this case, I don't think correcting negative exponents is not going to be as big of a deal here as I think they were with derivatives. So keep an eye out for problems that look like substitution but are not, and make sure that you're keeping an eye out also for these constant multiples here where we have to do a little bit of algebra. 9 times out of 10, if the substitution doesn't work right off the bat, all you need to do is multiply or divide by some constant. There are some exceptions to that rule, and we'll look at those in the very last video of this section.